Welcome to today's deep dive. If you are joining us, it is probably because you have that constant nagging curiosity about where technology is heading next.
You want to stay ahead of the curve.
Exactly.
Yeah.
Especially in the fast-paced world of generative AI. Well, you are in exactly the right place. Today, we are focusing on foundational, state-of-the-art developments. Specifically, we are exploring a really paradigm-shifting paper from researchers at Microsoft Research Asia and Zhejiang University.
Right. It's titled Hugging GPT Solving AI Tasks with ChatGPT and its Friends in Hugging Face.
Which is just a great title. And the premise here tackles one of the most persistent bottlenecks in current AI architecture.
Right.
Because we have these incredibly powerful language models, right?
Yeah, but they're fundamentally trapped in a text-only world.
Right.
They process text brilliantly, but they are essentially blind and deaf. I mean, they cannot directly interface with visual data or process audio streams natively.
Which is a huge problem for complex multi-step workflows.
Exactly. They can't execute multimodal tasks across different formats. So the researchers propose a fascinating architectural shift to solve this.
Yeah, and rather than trying to force one giant monolithic model to process every single modality, the paper suggests using the language model as almost like a centralized manager.
Brain.
A brain, exactly. It uses its mastery of natural language as a generic interface to route tasks to expert models housed within the Hugging Face community. So imagine your incredibly smart but blind and deaf friend suddenly getting access to thousands of eyes, ears, and hands.
That is a perfect analogy. We are looking at an architecture where the language model doesn't actually need to know how to generate an image itself or how to separate audio stems. It just needs to know who to hire for the job.
Which paves a completely new way toward artificial general intelligence, or AGI.
It really does. That managerial abstraction is the core innovation here. It's a highly scalable pathway because it leverages the massive, decentralized repository of specialized machine learning models that already exists on Hugging Face.
We don't have to wait for a single, unified, multimodal architecture to catch up to every edge case.
No, we just need to give our text-based models an effective dispatching system.
Okay, let's unpack this. Why exactly do current models struggle so much with these real-world, complex scenarios?
Well, the paper outlines three main limitations that create this bottleneck.
Starting with the obvious input-output constraint, right?
Right. The first limitation is the modality constraint you just touched on. Direct processing of vision or speech requires entirely different tensor representations than text.
You can't just shove a JPEG into a text processor.
You really can't. And the second limitation is the planning and scheduling deficit. Real-world tasks frequently require a chain of operations, like processing an image, extracting data from it, feeding that data into a speech synthesizer, and so on.
Which requires organizational capability.
And memory management that goes far beyond standard autoregressive text generation.
And the third limitation deals with zero-shot generalization versus fine-tuned expertise. We know models like GPT-4 are phenomenal at zero-shot reasoning across a broad domain.
Oh, absolutely.
But if I need to run a highly specific instant segmentation on a crowded medical scan,
a specialized model trained solely for that task will outperform the generalized model almost every single time.
right.
The generalized models are jacks of all trades, but they lack that surgical precision of domain-specific architectures.
So the breakthrough in HuggingGPT comes from a relatively simple but brilliant realization.
Yeah, the aha moment.
Every AI model, regardless of its underlying math or architecture, can be described using natural language.
Exactly. A description like, this model detects objects in an image, or this model converts English text to speech. That description acts as an API document.
So language becomes the universal adapter.
Yes. If you feed those natural language descriptions into a prompt, the central model can route tasks to the correct external tool based entirely on semantic matching.
It completely bypasses the need for the central model to understand the weights or the operational mechanics of the tool it's using.
It doesn't need to know how the tool works, just what it does. It's a massive shift from a monolithic structure to a compound AI system. The language model is just the semantic routing layer coordinating an army of specialists.
To see how this actually functions, the researchers designed a highly specific four-stage workflow. And I want to guide you through these four stages because it transitions this from a theoretical concept into a highly pragmatic system.
Let's do it.
Stage one is task planning. Looking at the mechanics here, it's interesting that they didn't just trust the model to figure out the workflow organically.
No, they couldn't.
They forced it into a highly rigid framework using what they call specification-based instruction and demonstration-based parsing.
Right, because relying on the organic creativity of a language model is actually a huge liability when you need deterministic machine-readable outputs. In stage 1, the model has to dissect the user's plain English request and output a structured JSON that defines the workflow.
And to enforce this, the specification-based instruction provides a strict template.
Exactly. The model must define 4 specific keys for every task. It needs the task name, a unique ID, the dependencies, which they label as dip, and the arguments, or args.
The dependencies key is critical there because it establishes the execution order,
It builds the timeline, yeah.
and the demonstration-based parsing means they are injecting few-shot demonstrations directly into the system prompt. They physically show the model several completed JSON templates to teach it the logic.
Right, they teach it how to break down abstract requests into a directed acyclic graph, a DAG of tasks. The few-shot prompting anchors the model's reasoning so it understands sequential logic versus parallel logic.
Now let's bring in a concrete example from the paper to see this in action. Say a user uploads a photo of a boy in a specific pose, and they ask the system to find that pose, generate a new image of a girl reading a book in that exact pose, and finally create an audio speech describing the new image.
That is a seriously dense multimodal prompt.
Very dense. But HuggingGPT Stage 1 parses that into 6 distinct, sequentially dependent tasks.
Right. Task 1 is pose detection on the original image.
Task 2 is text-to-image generation, but it's conditional on the output of Task 1.
Task 3 is object detection on the newly generated image. Task 4 is image classification.
Task 5 is image captioning. And finally, Task 6 is text-to-speech to read the generated caption out loud.
6 tasks. And once we have that cleanly parsed JSON, the immediate bottleneck becomes discovery, which leads into stage 2 model selection.
Because Hugging Face hosts hundreds of thousands of models.
Exactly. The central manager needs to assign a specific text-image model or object detection model to these tasks, but it obviously cannot load the descriptions of 100,000 models into its context window.
How does it avoid just getting totally overwhelmed? The token limits would be exhausted instantly.
Right. So the paper introduces a clever filtering mechanism. First, it filters the repository strictly by the task type defined in the JSON. If task 6 requires text-to-speech, the system immediately drops all vision models from the search space.
Okay, that makes sense. But even within the text-to-speech category, there are still thousands of options.
There are.
Yeah.
So to manage the remaining volume, they applied a top K filtering strategy based on community metrics. They rank the models by their total number of downloads on Hugging Face.
Oh, okay.
Yeah, selecting only the top 5 or 10 most downloaded models for that specific task. The system then feeds only those top K descriptions into the context window for the final selection.
Using download count as a heuristic is super practical. I mean, it assumes popularity equates to quality or suitability.
Right.
It solves the token limit problem efficiently. Though you could argue it might bias the system against newer models that maybe are more capable but just haven't accumulated the download volume yet.
It is definitely a trade-off. You're balancing discovery optimization with context window constraints. But it ensures the central manager only has to evaluate a handful of highly reputable options before making the assignment.
And once the models are selected, the system moves to stage 3 task execution. And this is a tricky scenario because the execution graph gets complicated.
Very complicated.
In our example, task 3, the object detection, cannot execute until task 2 generates the image of the girl. So how does the system handle the dynamic passing of data between these distinct external models?
The framework handles this through a mechanism called resource dependency. During the stage 1 planning, when the model generates the JSON, it uses a unique placeholder string for dependent arguments.
Which looks like less than sign resource greater than sign dash task ID.
Yes, exactly. That specific string acts as a logical lock. The execution engine sees that placeholder and knows it must wait for the specified task to resolve.
So it literally pauses the execution of task 3, waits for task 2 to finish, and then dynamically swaps the placeholder string with the actual file path or the tensor output generated by the previous model.
Precisely. And furthermore, any tasks in the graph that do not share these resource dependencies are executed in parallel to save time.
Right, if 2 tasks are just analyzing different aspects of the same static image and don't rely on each other's outputs, the execution engine just fires them off simultaneously.
Yeah, it minimizes latency. And it uses hybrid endpoints, meaning it can route inference locally if the user has the compute power or push it to Hugging Face's cloud infrastructure.
Here's where it gets really interesting. Stage 4 response generation. The expert models have run, and the system is basically sitting on a pile of highly technical robotic outputs.
Raw data.
Yeah, raw audio file paths, bounding box coordinates, probability scores, like it'll say giraffe with 99.9% probability.
Right.
The central model steps back in to synthesize all of this telemetry into a friendly natural language summary.
The language model ingests the execution logs and formats them into a coherent narrative. It translates the raw inference data into a user-friendly response, summarizing the entire workflow.
So instead of handing you an array of coordinates, it says, I successfully detected a book in the generated image and have created an audio description for you.
Exactly. It synthesizes the workflow.
Synthesizing bounding box coordinates into a natural language summary makes the output highly accessible. But I imagine there's a risk of data loss there.
Oh, for sure.
Because if the language model summarizes too broadly, the user might lose the precise analytical data the expert model generated. It's a delicate balance between readability and technical utility.
And that synthesis step relies entirely on the reasoning capability of the central manager, which brings us to the performance and the quantitative evaluations.
Yeah, let's put it to the test. How well does this actually work in practice?
The researchers rigorously tested the framework across single tasks, sequential tasks, and highly complex graph tasks. Those are the workflows that branch out into multiple interlocking dependencies.
And the comparative results were pretty stark, right?
Very stark. They tested proprietary models against open-source alternatives acting as the manager. GPT 3.5 and GPT-4 absolutely crushed open-source LLMs like Alpaca 7b and Vicuna 7b in the task planning phase.
Wow.
Yeah, the open-source models at the time simply couldn't reliably map the complex JSON logic required for multi-step DAG. The gap in reasoning capabilities becomes glaringly obvious when you ask a model to structure a dependency graph rather than just write a creative essay.
But the evaluation methodology itself is really fascinating here, because grading a multi-step logical plan isn't as simple as checking a math equation. To evaluate the graph tasks, the researchers actually utilized GPT-4 as an automated critic.
Right. Having a language model act as a judge to evaluate the outputs of other models is a massive shift in AI research.
They fed the generated task plans into GPT-4 and asked it to score whether the plan was logical, resource efficient, and actually addressed the user's initial prompt.
Because relying on human evaluation for thousands of complex graph outputs is prohibitively slow and expensive.
Yeah.
LLM as a judge is becoming a standard methodology.
But they didn't just trust the AI judge blindly.
No, they did back up the automated critic scores with extensive human evaluations to ensure correlation. And the human experts confirmed that the proprietary models were vastly superior in rationality and success rates for complex routing.
Let's zoom out a bit and look at the broader landscape of autonomous agents. The paper compares HuggingGPT to other famous frameworks you often hear about in this space, things like AutoGPT, AgentGPT, and Baby AGI.
Right. And the fundamental difference lies in their approach to planning. HuggingGPT utilizes global planning, whereas AutoGPT relies on iterative planning.
That distinction is critical. Iterative planners operate step by step. They analyze the prompt, decide on step 1, execute it, observe the result, and then use that observation to plan step 2.
It uses a reflection mechanism, often referred to as a react, loop reasoning, and acting.
Iterative planning sounds incredibly adaptable on paper, but in practice, it often falls into what's known as the reflection trap.
Yes, the loop of doom.
Right. If the agent makes a slight error in step 2, the reflection mechanism can misinterpret the error, causing the agent to get stuck in an endless, looping hallucination trying to fix a problem it doesn't even understand.
HuggingGPT bypasses the reflection trap entirely through global planning. It generates the entire task queue, all the dependencies, all the routing in one single initial query before any execution begins.
It maps the entire route before putting the car in drive.
Exactly.
Yeah.
The trade-off is that global planning lacks real-time adaptability. If step 2 fails in HuggingGPT, the system doesn't pivot. The subsequent steps just fail sequentially.
But when it works, it's far more efficient. And there's also a significant difference in the tool sets these agents use. AutoGPT typically relies on basic generalized tools, like executing a web search or running a Python script.
Whereas HuggingGPT is deeply professional. It's integrated into highly specialized state-of-the-art machine learning models. It's not just running a script, it's invoking a specialized diffusion model or a neural network for visual question answering.
It's using surgical instruments instead of a Swiss Army knife.
Beautifully put, yes.
Now, to ensure we get a balanced view, we need a reality check. The authors are very transparent about the limitations of this architecture. What are the specific flaws they identified?
Well, they noted 4 major limitations. The most glaring one is that the entire system relies heavily on the intelligence of the central language model.
The manager.
Right. If the manager misunderstands the prompt and creates a flawed JSON plan in stage 1, the execution engine will flawlessly run a terrible workflow. The success of the whole thing relies completely on the competence of the central router.
If the manager plans poorly, the whole thing breaks. What's the second limitation?
Efficiency and latency. Having the language model parse the prompt, query the model descriptions, structure the JSON, and then initialize multiple heavy inference tasks across different servers takes significant compute and a lot of time.
This is not a low latency architecture. You're not getting sub-second responses here.
Definitely not. The third limitation brings us back to the maximum token length constraint. The top K filtering trick works for now, but as repositories like Hugging Face grow into the millions of models, summarizing the landscape to find the optimal tool becomes mathematically impossible within current token limits.
Especially because the system prompt is already heavily loaded with those few-shot demonstrations before it even begins reading model descriptions.
Exactly. And the fourth limitation involves the sheer instability of extracting structured data from generative models. Language models are fundamentally probabilistic text generators. Even with strict instruction, they hallucinate.
A single rogue comma in the JSON output.
Oh, it's fatal. Or if the model decides to be conversational and adds, "Here is the JSON you requested," outside of the code block, it instantly breaks the downstream parsing engine.
The system requires deterministic formatting from a non-deterministic generator.
Which introduces inherent instability.
So what does this all mean for you, the listener? The overarching takeaway is a massive shift in how we approach multimodal AI. For a long time, the assumption was that reaching the next plateau of capability required training a single, gargantuan, unfathomably expensive model that natively understood text, video, audio, and spatial data.
One model to rule them all.
Right. But HuggingGPT proves that we can achieve incredible multimodal AI right now simply by teaching a smart language model how to be a good manager of existing specialized tools. You don't necessarily need a smarter, all-knowing worker. You need a highly capable manager to coordinate the specialized tools you already have. It's a highly scalable blueprint for future AI systems.
It forces us to rethink the trajectory of agent architectures. I want to leave you with a final thought to mull over.
Great.
The system currently relies on the central manager reading descriptions to assign tasks to existing models.
You're right.
But what happens when the central model encounters a complex niche task for which no expert model exists in the repository?
Oh, wow.
Given the rapid advancements in code generation, could the next evolution of this system be an LLM manager that realizes a tool is missing, writes the code to train a new specialized model on the fly, deploys it, and then hires it to complete the user's original request?
An agent that dynamically expands its own toolset by generating and training the very experts it needs to hire. That is an incredible concept to consider as these compound systems become more sophisticated. Thank you for joining us on this deep dive. Keep questioning the architectures, keep exploring the edges of what's possible, and we'll catch you next time.